Okay, this is a rather lengthy lesson, and I'm going to try to make these things clear to you. It's a lot of complicated things that you probably never did before, so I'm hoping that everyone watches all of this lesson. I have no idea how long it's going to be, but I did it in advance. I made the screens in advance, and it took 3 different screens to do this lesson. So let's just get started. This lesson, problem set 32, is called, like very many pages here, inverse functions, 4-quadrant sines, and inverse trig functions. So we're going to start out with the simplest one, is the inverse functions. Now here we have our function machine that you've had probably ever since you were in like 5th grade. Here's our machine right here. So if we put a 2 in our machine, we take it times 2, we subtract 1, and a 3 pops out. If we put a 4 in our machine, a 7 pops out, etc. Now, every one-to-one function has an inverse function that will let us go the other way. So there is this is a one-to-one. Remember, if we put a 2 in and we get 2 answers out, that's not a function. If we put a 2 in and get a 3 out, and then maybe put a 4 in and get a 3 out, it's still a function, but it's not a one-to-one function. So one-to-one, you can just see how it looks like one-to-one. We don't have 6 going to 11 and 4 going to 11. It's one-to-one. So first of all, it has to be a one-to-one function. Then it's going to have an inverse function. What an inverse function is it reverses whatever you did. So if we put the 11 back into an inverse function, this is an inverse function, if we put 11 back in, we should get 6 back out. So it's just reversing it. See how we multiplied? Down here we're going to divide. Here we subtracted, here we're going to add. So the way you find it is, we're going to get into this in a minute, but you set it equal to y, and then you solve it for x, and you get your inverse function. To find the inverse function of a one-to-one function defined by an algebraic equation in which y is a function of x, we're going to use a 2-step procedure. So as long as you remember the procedure, it's not very complicated. And they don't give you very hard problems in this book either. So here we go. To find the inverse function of a one-to-one function defined by an algebraic equation in which y is a function of x, we use this 2-step procedure. So we're going to solve the original equation for x, and that's what I did up here. You can see up here I solved the original equation. Here's the original equation. I solved it for x, and then you're going to replace every x with y and every y with x. So you can see up here, this was the original function, y equals 2x minus 1. I solved it for x, and then I replaced this x. I replaced this x with a y, and I replaced the y with an x. And that's what we have right here. That's the inverse function. Now graphically, if I would graph the original function, which is right here in red, that's the original function, and then I would graph the inverse function, it reflects over the line y equals x. So here's y equals x. The slope is 1, 1, 1, 1, 1. And it's going to reflect, the red line is going to flip right over and land on the blue line. So every inverse function is going to be a reflection of the original function over the line y equals x. So let's try a problem. It's not like this is difficult, it's just new. So we want to find the inverse function of y equals negative 2x plus y. So the first thing we're going to do is we're going to solve this for x. So here we go. I'm going to add 2x to both sides, so we get 2x. And let's subtract y on the other side, minus y plus 5. We divide everything by 2 until we get x equals negative 1/2 y plus 5 over 2. Finally, that's your first step. There's still only 2 steps. The second and last step is replace the x's with the y and the y with the x. and this is our inverse function. Now later we're going to use function notation, and to denote an inverse function it's going to look like that. It has this little -1 up here, like that. And that just tells you that it's the inverse function. Now if we were to graph these two lines, they would reflect over the line y equals x. So they give you two examples in the book, but I don't think that we need to do those examples. You can also see the graph of this one in the book. Alright, that's it for screen 1, so let's go to the next part of the lesson. Alright, signs of trig functions. So, trig functions each have a sign, and there's a way to remember them that the book gives, and I think it's pretty good. If I draw these little triangles, it's all kind of messy in here, so I just want to try to conserve space. But here I drew like a bunch of right triangles, one in each quadrant. So if we're going to find, say, the sine of theta in the first quadrant, it would be opposite over hypotenuse. The hypotenuse is always positive. So that would be positive, right? Opposite over hypotenuse, positive over positive. And you can see if I did sine, cosine, or tangent, we can't even get a negative. There's no negative. So all of the trig functions are positive in the first quadrant. Second quadrant, if I did the sine, opposite over hypotenuse, it's going to be positive. But if I do the cosine, adjacent over hypotenuse, I'm going to get negative. And if I do the tangent of theta, I'm going to get opposite over adjacent, and that's going to be negative. So the only one that's going to be positive is the sine in quadrant 2, and that's why this is the way they have you remember it. All students take calculus. So they're all positive in quadrant 1. Only sine is positive in quadrant 2. Only tangent is positive in quadrant 3, because the sine of this angle would be opposite over hypotenuse, so that would be negative, and the cosine would be adjacent over hypotenuse. So the only one would be positive would be opposite over adjacent. Positive, negative over negative would give you the positive. So only tangent is positive in quadrant 3. And then finally in quadrant 4, the only one that's positive would be cosine, because it would be adjacent over hypotenuse, so it would be positive over positive. All the other two would be negative. So it's just something to keep in mind, signs of trig functions. Now, what we're going to get into now is the inverse of, we did the inverse of algebraic functions. Now we're going to do the inverse of trig functions. And this is where it gets kind of messy. So hopefully this is moving pretty quickly. Inverse cosine functions. We're going to do each one of them. We're going to do the inverse of the cosine, inverse of the sine, and inverse of the tangent. And they're going to start, once you get one, you kind of get the rest of them. Now remember, to find a function, your output, you can't have a 60 degree, you can't say what's the sine of 60 and get more than one answer out, or it's not going to be a function. Remember, a function, whatever you put in gets a unique number out. So our problem comes when we try to find the cosine of 60. Oops, hold on a second, my battery is not charging. Figure out where my problem is here. Okay, we're good. Okay, so 60 degrees, you're going to get the cosine of 1/2. No matter no matter which angle you're going to use, it's going to be, if you use 60 degrees, it's going to be 1/2. Or if you use the cosine of 300, it's still going to be 60, it's going to be a half. Let's see. We can turn these around and ask for the angle whose cosine is 1/2. So I could say, what is the angle whose cosine is 1/2? And that's our inverse. You either call that the arc cosine or the cosine to the -1 degree, inverse cosine. Hold on, I'm having writing problems now. So cosine to the -1/2. These are going to be the inverse functions. So we've kind of talked about this before when we were doing polar notation. that we can take and find. If I give you the sides and ask you to find the angle, that's finding the inverse. Both of these statements refer to the inverse cosine of 1/2, and both mean the angle whose cosine is. So if I said the arcsine of 1/2, you would say, okay, what angle has the cosine of 1/2? Now here comes the problem. There are many positive angles whose cosine is 1/2. So if I said find the angle whose cosine is 1/2, right away you think 60. But here's the problem, and I just took a picture of this out of our book. Here's the problem right here. 60 would give you, if we took the inverse cosine, we would get 60 for this angle. And also, you could go around once and then another 60, and that would give us 420 degrees around, and that would give us the cosine, the inverse cosine of 420 is also, the cosine of 1/2 is also 420 degrees. And if you go around twice, the inverse of 1/2 could also be 780 degrees. And we could do the same thing, go in the negative direction. The arc cosine of 1/2 could be 300 degrees, it could be 660 degrees, and it could be 1020 degrees, depending on how many times you go around. And it could keep going and going and going as many times as you want. So if I said find the inverse of cosine of 1/2, you're not just getting one answer out, you're getting out infinite number of answers. So what that means is we have to limit our range. So let's go back up here. The first one I'm going to spend a little bit more time on. When we get to sine and tangent, we won't spend so much time on it. Since there are multiple angles for every domain value of an inverse cosine, the inverse cosine is a relation but not a function. When they ask in the book for an inverse cosine of a number, they would like to have only one answer, so that the inverse cosine will be a function. So we have to limit the angles that we find our inverse cosine in. So only the angles that we're only going to consider the angles between 0 and 180 inclusive. So when they ask you to find the inverse cosine of 1/2, it's only going to be the angles that are found in quadrant 1 and 2. Does that make sense to you? Because if we use any other, if we add the fourth, or if we keep going around and around, we're going to get more answers out than one. Functions, you put one in, you get one out. The book uses a lowercase cosine or arcsine to mean inverse relation. That means you could get more than one answer out. And it uses uppercase letters like this, cosine of -1, or arc cosine, to mean the inverse function. That means you're going to limit the range. It's only going to be between 0 and 180 if you have the capital letters. Thus, if we choose a domain of 1/2 for the inverse cosine function, then it's only at the angle between 0 and 180 inclusive. It means it's going to include 0 and 180. Okay, quickly we'll do the sine function. It's the same thing. If I ask you for the inverse sine of 1/2, which means the angle whose sides are 1/2, you're going to get multiple answers. You're going to get this. You're going to get 150 degrees, or you go the whole way around and get 510. If you go around 2 times, and it could be the angle 870. Therefore, when they ask for the inverse sine of a number, in order to have only one answer, and thus have a function, we have to limit the angles. Now this one's different. For cosine, it was between this range right here. It was this range. For the sine, it's going to be this range. Angles only in the first and fourth quadrant. And that's inclusive as well. Okay, and finally the tangent. It's the same idea as the sine and cosines. You could get the angle in the first 360 degrees, and then you can keep going around and around and getting more angles. The angle range for the inverse tangent is the set of all angles between -90 and +90 exclusive. So when we're talking tangent here, it's just going to be these two, this range between here and here. And it's exclusive because you're going to get undefined at -90 and 90. So it's only going to be the angles within here, the first and fourth quadrant. Okay, now we're going to try some examples. Hopefully you're not so confused. It's not as complicated as it looks. So let me just bring up some examples here. And then we're done. Okay. I can move this over. Examples. These are kind of strange, but we'll give them a try. Okay, we want to evaluate the arc sine, or what we, I like writing it like this better, the inverse sine of square root of 2 over 2. So what that's saying is what angle is square root of 2 over 2. So the first thing you need to do is you need to put this back. This was rationalized, so you need to kind of unrationalize it. So square root of 2 over square root of 2, and we're going to get 2 over the square root 2 square root of 2, and that's going to be 1 over the square root of 2. And you should probably already recognize when you have the square root of 2 over 2, it's going to be the 45-degree angle. So for this one, I went through like 5 pages in the book pretty quickly there. For this one, we're talking about sine, and sine is just in these two quadrants. So we're trying to find which angle it would be, and so it would have to be in this quadrant right here. So this would be, it would be this triangle, our 45, 45, 90-degree triangle. So this would be our 1, 1, square root of 2. So when they're asking for the arc sine or the inverse sine, they're asking for what is this angle right here. And you look at it and it's just 45 degrees. So the arc sine of square root of 2 over 2 is just 45 degrees. Alright, next one. Evaluate the arctan of -1/3 square root of 3. And again, we need to unrationalize the denominator. So you have negative square root of 3 over 3. We unrationalize it, and we get -3 over 3 square root of 3, and we're going to get -1 over square root of 3. So here's our triangle that we're going to use. It's our 36 and 90 degree triangle. And we want opposite over adjacent. So our angle is going to be 30 degrees. So this angle right here. So we have to pick, this is arctan. Remember, arctan we're going to evaluate in these two quadrants. So the angle has to be this angle because it's the only one that is negative. This thing is negative, so it has to be down here. So it would be negative, and we went down, so this would be 1, let's see, this would be 30 degrees. 1, 2, square root of 3. So if we set it up like this, if it's going to be negative, it has to be in this quadrant, and so the degree of that angle is 30 degrees. So hopefully that makes sense to you. I think we've done this before, so it's not that hard. The only thing different is we're going to put it in different quadrants because of this negative sign right there. Okay, here's where it gets a little dicey. This one is find the cosine of the arctangent of -3 over 5. So they want you to find the cosine of an angle whose sides are -3, 5. So on these, do this inside part first. We're going to set this triangle up. So I'm going to set this up. This is arctan would be opposite over adjacent. So that means we're going to do, if our angle is, our sides are going to be -3 over 5, we have to fill in that triangle. So our negative is going to be down here, right? Because it has to be in these two quadrants. negative 3 over 1, 2, 3, 4, 5. So I'm going to set my triangle, put my point right there, and I'm going to draw this. This is negative 3 right here over 5. Okay, opposite over adjacent. And it has to be, the 3 has to be negative because it's the whole thing is the only way to make this fraction negative. Okay, what we have to do is find the cosine of this angle. Here's the angle right here. We want to find the cosine of this angle. We don't actually have to figure out the angle yet, because when we do the cosine, we really just need the sides anyway. We don't need to figure out what the arctan, what that angle actually is. We just need to draw the triangle. Then, in order to find the cosine, remember cosine is adjacent over hypotenuse, so we need to find the hypotenuse of this triangle. So it's just 5 squared plus negative 3 squared equals c squared, and we get 25 plus 9 is 34 equals c squared, so we can get c equals the square root of 34. Now we can actually answer the question. We want to find the cosine of the arctan. So once we set up our triangle, we can find the cosine of this angle. That's what they're really asking. They're saying find the cosine of this angle. So right now we don't even need to know the angle. So we would say the cosine of this angle is adjacent over, cosine of that angle is adjacent over hypotenuse. And then finally all we have to do is rationalize that just to make it legal. And we get 5 square root of 34 over 34. And that is the cosine of the arctan of negative 3/5. Let's try one more of these and then we'll be done. Same idea. Evaluate the sine of the inverse cosine of 2/3. So again, we're going to set up our triangle. This is the arc cosine this time. So both of them are positive. So we're going to come out here. Cosine is opposite over hypotenuse. So we're going to come out 2. And we don't know yet. We know this is 2. We don't really know this height yet, but we know this is 5 because this is the, whoops, yeah, it should be adjacent. This is adjacent over hypotenuse. So the adjacent is 2, the hypotenuse is 5. So we need to find this missing side yet. So we use the Pythagorean theorem. So we would say 2 squared plus b squared equals 5 squared. And that would be b squared, 25 minus, let me just do this out, can't think that fast. So we get b squared equals 21, and I'm doing something different here. Oh, I forgot that I didn't subtract it. 25, that's right, 25, hold on a second, oh that should have been a 3. I put in the wrong numbers. I can't read my writing. How bad is that? Okay, so this is 3, this is 9, here we go, and then this is going to be, sorry for all my scribbling, 5. So b is going to end up being the square root of 5. So right here is the square root of 5. So once you set this one up, you're just setting the triangle up. You don't even need to find this actual angle, because when we do the sine, we're doing the sine of the angle, which is really what we need to know are the sides. So finally, we can say the sine of theta equals opposite over hypotenuse. And that is the answer to this whole thing. It's equal to the sine of the arc cosine of 2/3. So we're really saying what's the sine of this angle is square root of 5 over 3. So hopefully that was all helpful, It's hard, it's a lot of information. So we'll go over this in class on Thursday. That's it.